Thanks a lot. Good morning, everyone. Let's check. There we go. All right, so I'm here to talk to you a bit about Bender, which is a dependency management tool that we've been developing here at ETH as part of the Pulp project. It's designed to tackle a few very specific design needs that we have in doing ASICs and developing IPs. If you've ever worked with any form of the Pulp platform, we have a big collection of IPs which are spread across a lot of different Git repositories, and we have to somehow collect these things together and arrange for a proper build. So this is where this whole Bender story comes in. So basically where we started out back in the day when the whole Bender project started is we had this IPApprox slash IP tools, IPs tools set up, which was a Python-based, home-baked solution to collect IPs and manage builds. And basically, this thing had a few shortcomings as the project grew and the number of repositories exploded. There was no distinction between IPs and chips. So it was very difficult to convince the tool that you're working on, for example, a small AXI adapter which you want to integrate everywhere else, or you're working on a chip where you want things to be very stable and reproducible. Part of this problem was that there were actually no transitive builds and transitive dependencies, so there was no way to actually declare that an IP itself uses another IP as a kind of dependency. So when you built a chip, for example, or had a top-level design, you had to pull in all the dependencies yourself and perform the dependency resolution on your own, which was great and worked well in the beginning, but as the project grows, it becomes hard to do that. And there were all the few things, like we had the tool always embedded in the repository, the IPs kind of, it was confusing whether the user was working on the IPs managed by the tool or it's the other way around. So this is where Bender came in, which is basically a replacement tool to fix these issues, which some of the PhD students in the lab actually came up with. And we wanted to have a very small tool to kind of tackle the issues that we saw. If you want to give it a try, like the only takeaway point from this talk should be the repository and binaries, if nothing else. This you can find on GitHub. We provide the source code, you can build it yourself, and we have some pre-built binaries that you can run yourself. Otherwise, use Cargo to build it if you have a Rust build system, and otherwise you can also build from source directly. So yeah, if you haven't guessed, it's actually built in Rust, which is like a very nice nerdy angle to the project. So basically the wish list, what do we want to achieve with this thing? So first and foremost, we want to have these transitive dependencies so we can resolve the dependency graph automatically. We want it to be tier-based and hands-off and kind of opt-in. So basically, when you want to use the tool, there should be nothing the tool forces upon you that you don't want to do. Because usually you have a very well-established flow for your ASIC stuff, for your FPGA stuff, and if you pull in a tool which kind of throws everything overboard and wants to do things in its own way, then this might be hard for you to adopt. So basically, we separated Bender into these tiers, which work on their own, and the next tier builds on the previous one. So basically, you have, as a tier 1, there's package dependency resolution, which is you give it a few Git repositories, each repository can link to other repositories, it will do resolution and give you basically a checkout of those repositories. End of story. Now, if that's sufficient for you, this is the tool you can use, and you never need to touch other features. On top of that, if you're actually building ASICs, it might be convenient for you to collect the source files automatically. So there's another tier on top which allows Bender to actually gather source files, RTL files for you, and collect them. And as a kind of third tier, you can have the tool automatically also generate scripts for your tools and feed into the tools, which builds on the previous 2 layers. One thing we also wanted to do is not have a central registry where everything goes together. So the tool is actually built around this notion of everything is specified with full Git URLs. Most of them are currently on the GitHub Pulp project, Pulp platform organization, but you can have them on your own. You can point them into your internal GitLab servers, which is what we do frequently. So there's no kind of public repository you have to adhere to. And we want this to be tailored to an ASIC flow. So it should be ultra conservative when updating IPs, because you don't want to be in the process of actually making a chip and then the tool changes something underneath your feet and everything breaks. And you have to go back and do all the verification again. And this kind of reproducible builds also goes into this. So you want to be sure that once you've taped out a chip, you have a clean understanding of what version of which IP was actually in the silicon. And kind of as a last thing, which is more of the development angle, we want this to be wanted this to be written in a compiled language because we've written things in Python before, and this works really well and it's easy to adjust. But it's easy to make mistakes which you only find at runtime if you don't use some elaborate static checking, and even if you use that, there's some runtime errors which you need to weed out. So we wanted to try an angle where we have a lot of static checks up front. So we don't mess up the tool easily. But this is kind of a meta point. So tier number one, the first step basically in this whole Blender flow is the transitive dependencies, which is an improvement over our previous tool flow that we had, which had the problem that the IPs could not declare the dependencies themselves, and there was no standalone building for an IP. So say when you wanted to have, for example, an AXI interconnect, which used some other IPs, etc., you just wanted to have a test bench run for that interconnect. That was pretty hard to do because you always had to set up this kind of chip repository which pulled in all the dependencies. And we want to move towards like this turnkey push-button testing solution where you can test individual IPs very easily. So basically, let's say you're building a chip project. For the way it was before, you had a chip, which was called Tosca here, for example, as a kind of example. And then this thing pulled in a lot of dependencies, clustered RISC-V core, some AXI stuff, some AXI slicing, etc. And that was actually that was the thing. So in here, when you built the chip, you had to know all the dependencies, which this graph could grow quickly as the chips evolved. So this was the old state, and we transitioned with Blender to this scheme where if you're building a chip, you're just declaring your primary first level dependencies. So you're building a chip, someone else has already built a cluster with processors, and you don't want to go in and track all their work again. So you just declare that cluster as a dependency. Same with the AXI slice and this AXI crossbar, for example. And then these, again, on their own can depend on other things like a collection of standard cells like FIFOs, etc. So one of the problems we had in this whole setup, because we're using Git for this whole thing, and we're throwing a lot of the hashes and commit-ish around, is as soon as you start doing these transitive dependencies where you're not providing the absolute truth as the designer up front, which packages are to be used, you run into this trouble that when you have two packages, depending on the same other dependency, but they specify different hashes, it's really hard to tell if the commits are compatible in this kind of meta way of, will this break my silicon? And it's hard to pick which one would be best and which one remains compatible. So the solution for us was to move towards semantic versioning, which is very popular in software package managers like NPM, I think, uses it, Cargo uses it, etc. So the basic idea is it's a version as you know it, and everyone has been using it, but it kind of formalizes a bit what the individual parts of the version number mean. And so the gist of it is there's basically a major version number, a minor version number, and a patch number. So there's always three fields. Whenever you break something in your design, so you make a change to your IP, which will require someone using it to actually do active work on their own to fix their design to work with yours again, then you bump the major version. If you do a change which is backwards compatible, so someone using it does not need to do any work, it just works out of the box, you bump this minor version. Then if you do basically just a fix for a bug, or you fix some behavior, you actually just bump the patch version in the back there. And this works really well. It's coming from the software world, and there's kind of a caveat here. With HDLs, it's actually very easy to introduce breaking changes. If you think about, for example, port lists and system Verilog, if you add features to the hardware, to an IP, it's very common to actually require additional ports in the port list. And with HDLs, like System Verilog, many tools don't support default port assignments, for example, so a lot of these changes will be breaking by default. So you have to work around that a bit. But this is the versioning scheme we've adopted for Bender, which we've taken from the software world, and it's served us well. So we also use and encourage a lot of changelog tracking. So if you look at the pulp IPs, you will usually find the changelog file where we keep track of what we actually do with the corresponding version number and the dates published, so you can actually understand what we're doing with the IPs and how they change. So basically, this takes us to with a way of resolving dependencies and making sure that we don't break your build if you depend on an IP. One thing that the next step basically is having reproducible builds, which is that when you've done a tape out and something has gone into silicon, you want to know exactly what IP version was taped out, what the exact source code that was in the IP. And went into silicon. There's many ways to do this. You could, for example, just archive all the source files, and that works really well as well. But the software actually faces this problem as well. So there's projects like Composer or Cargo, which have this problem as well. They want to keep a manifest of what went into a build to be reproducible. And the solution is that they adopt is log files. And basically, a log file is just a copy of the manifest. The manifest is the file that you write with the information on the IP and all the dependencies, etc. It's a copy of this file with all the dependencies locked to a very specific hash of the IP and the content, which is really nice because in Git, this is a hash over via some indirection over the exact contents of the files in the repository. So this is actually a very nice way to lock down the content and find the content again. So where you would write something like version 1.01 or some branch name in the manifest, the log file would then contain the actual exact version that was used. And another thing that basically plays into this is dependencies only update to resolve versioning conflicts, and they only update when you ask for the update explicitly. This is to make sure that while you're developing and actually verifying your silicon or your builds, the things don't start changing underneath your feet, which is a very annoying thing to happen and can lead to silicon bugs, which are not fun to have. All right, so dependency resolution, this is how the whole tool basically works. How do we go about this? So basically, we go through each dependency and we determine which version to use. I mean, that's the kind of the recipe of what we want to do. And then we go in and for each dependency, again, we do this recursively until we have resolved everything. Now, that part is kind of tricky because you need to, the graph can grow, as I'll show in a minute, which makes it kind of cumbersome and tricky. But basically, semantic versioning helps here because the dependencies themselves, when they specify a semantic version as a dependency, this is basically a version range. This gives you a fairly big range of options for each IP to pick, and all we have to do is find basically the set of compatible versions and then probably pick the newest one, which is usually what you want to do on the newest versions of the IPs. So the way we do this is we make a table of that, of the available versions, and we start crossing things out, backtracking, etc., to find a solution to the dependency graph problem. And again, as a hardware developer, you don't want to do this usually yourself, also as a software developer. Previously, we had to do this ourselves with the previous tool, and now we can automate this process. So here's how it works, basically. Say we have a dependency graph, which is fairly simple. You have a package A. It depends on version 1.0 of B, on version 1.1 of C, and package B also has a dependency on another package D, which is version 1.1. So as I said, we don't really have the central registry, which already contains all the versions of packages available, and you can just pull in and you get kind of a already complete view of the dependency graph. We don't collect the whole graph information a priori from the Git repositories, because as I said, we want to have the ability to just pull in Git repositories as dependencies. But then when you think about it, the Git repository contains the manifest with other dependencies and source files, and that changes as the IP evolves. So what you would have to do is actually go in and find every change to the manifest and collect each version of the manifest file to build this kind of version-dependent graph of the IPs. And this is kind of not feasible to do, or it takes a long time. It's prohibitive to the user. So what we do is basically we discover dependencies on the fly as we resolve the dependencies. So what we do is we build a table and we start out with the root package. So package A, and package A is version 1.0. There's just this version. So we pick that version. This is the current best solution to the problem. Now we go in and look for dependencies of package A, which in this case is B and C, and we note down all the available versions in that repository. So basically, as soon as we have picked the version here, we go in, we pull in all the dependencies via Git, and we look at the manifests in the dependencies and pull in all the versions which are available, and we add these to the table. Then we go in and cross out all the versions which are not compatible. So version C is specified as needing at least version 1.1 to be compatible. So version 1.0 already is off the table. So we cross that out. And then we pick the best available version of the packages. And then we go ahead, we add in the next layer of dependencies. We note all the available versions, and then we cross out the infeasible ones, and then we pick the final solution. And then this is kind of the solution to the dependency resolution problem, and we store this in the log file as a kind of result that you can check into your repository for chips, for example, so you have a grasp on what's happened. Now, the way how this can become a bit problematic and where the backtracking comes in is that if you have other dependencies which limit, for example, the upper bound on the version of an IP. So this could be, for example, that you're working with version 1.0 or 1.1 of an IP, and the owner actually published version 2.0 at the moment. But these things are breaking changes, so we can't just update you to version 2.0, so we kind of have to be careful, and the newest version is not always the one which is actually compatible with what you're doing. So the problem there is that, okay, we start out again with package A, it's version 1.0, we pick that, and then we kind of fill in again the available versions for B and C. We cross out, due to dependency requirements, the versions which are not feasible anymore, and we pick a version of the packages, which in this case is just 1.3, 1.1, whatever is compatible and the most recent. Then we go in, we extend the dependency graph, we collect the repositories, and we make a list of the available IPs. In this case, D has a version 2, and E has a version 1. So again, we do this crossing out of unavailable options, and then we pick something. Now, the problem is that B itself has E depends on B, but it requires the version to be less than 1.2. So the version of B, which we've already picked, is no longer feasible because we weren't aware of that requirement and that constraint when we built up the graph, but now that we've extended past all the packages, something came in view and in range, which kind of retrospectively crosses out some parts of the table. So what we have to do is we kind of have to disable all the solutions again that we based on this pick back there, and do another pick. And then in this example, because package B depends on version 1.2 of D, we have to cross out some options of D, and then we have to pick some version of D, which is not the newest. So this is where the whole backtracking comes into play, and this is basically a result of this problem that we collect dependencies iteratively and expand out. Okay, so that's the whole dependency resolution story. Now, there's the next step we can do. The dependency resolution gives you basically a checked out version of all the repositories and make sure that if you adhere to semantic versioning, nothing breaks, and you have known semantics of how things work. Now, on top of that, we build another tier, another layer, which is we can actually collect source files for you, which is in HDLs, you would probably, when you assemble a chip, you would probably in some way collect all the RTL files for your IPs, for synthesis, etc. So now that we have established the dependency tracking as a first tier, we can track the source files in each IP as well, which is another section in the manifest, which is called sources, where you can list source files in compilation order. And there's more to that. You can group them, etc. But this is how we do. So, for example, you can group things. You can add include directories, defines. This all apply to the source files which are underneath that. And this allows you to also describe what source files are inside the IP and what source files you need. So this is the second tier. What we can do based on that information is actually build a compilation recipe, which is kind of tool agnostic, because chances are that there's some order dependency inside the source files, which all the tools you need to maintain to feed the tools. So what we can do is we can basically take the dependency graph, which is resolved, we can do a topological sort over it, and then concatenate all the source files in order. So if this is your dependency graph, we can do a topo sort, which is basically this, what you get when you type in vendor sources, which gives you the source tree of the order source tree of your entire project, and you get basically a topological sort of the files in compilation order. So again, this is not something you want to do by hand, and it's nice to have the tool do this for you, but this is kind of opt-in. This is the second tier of the tool, so if you don't need that, you don't need to use that. And then there's also other features that are available, for example, targets, which have a specific use, and that is that we have different source files for different technologies, like we're targeting some ASICs, there's different ASIC targets that you need to support. You're targeting FPGAs, there's different vendors and architectures, and then there's different use cases. You want to do RTL simulation, RTL synthesis, where you don't probably need any verification IP. You want to do simulation of post-synthesis, netlists, post-layout netlists, linting, etc. So you have a huge use case and different needs that your source file set has to fit. And this is where targets come in. Targets are basically flags, Boolean flags and expressions that you can add, which limit the set of targets where the source file is active. So for example, you can have in your source files a FIFO implementation, which is FPGA optimized. And if you mark that with target FPGA, source file will only be used when you're actually building for an FPGA. And you can also do the opposite and say, okay, here's a generic implementation which you're to use when there's no FPGA target. And there's kind of a very simple like expression syntax built around that you can use to clearly specify what you're doing. And we use that to kind of isolate out synthesis-specific things, simulation-specific things, so we can have one manifest and one source listing, basically serving all those needs. Yeah, so for example, this is just to give you a quick overview over how Bender looks in the reality. So you would create, for example, an individual small IP, for example, a common cells collection, which contains FIFOs, etc. So you create this bender.yaml file, which is the manifest. You specify some information about the package, and you list some source files. This is how things would look like. This is like your typical Bender IP. Then you can take things a bit further by saying, okay, now let's do an IP which requires other IP packages to function. For example, a RISC-V core. This is our RISC-V core, for example. And what we do is we add this dependencies section where you can list other packages, specify where they're coming from. They can be local paths, Git repositories, URLs, specify a version which you're supposed to pick on top of that. And then there's entire chips that you can build, which is basically a bigger project, which actually looks pretty much the same as any other IP, with the key difference that now you're actually committing the bender.log file. Usually you want this to be in your git ignore, and you don't want to commit that for your IPs, because this is just kind of a thing which is only applies to actual chips. But when you're doing a chip itself and the tape out, you really want to commit this log file, because this nails down whatever the version was of the IPs tape out. So as a kind of last step, just quickly gloss over this, is you can actually also have Bender feed the tools. So we now have all the source files in the dependency graph. We have the dependency graph itself, but now we need to feed all these tools: vsim, antisim, the Synopsys toolset, Cadence, etc. So this you can do manually. You can call Bender sources. It will give you like a JSON representation of your build tree, and you can feed this into your tools if you feel like it. But you can also have Bender do that for you. And the way we do this is we do script generation. So Bender can actually emit some tool scripts for you. This includes mainly analyze scripts for Synopsys and compile scripts for the QuestaSim simulator. So this is how you would do this. You would call Bender script and then a format, and you can pipe this in. to a file, and this comes in various flavors, but most of the tools use Tickle, and you get basically a nice compilation script out of that. And the same thing if you want to do use a Synopsys Design Compiler. The cool thing here is that this you can actually check into version control, which helps collaboration with other tools. There's some experimental support we've started to add for Edelweiss, which is actually a pretty nice thing, which can take over this part for you, and you kind of feed into a bigger ecosystem of available targets. So this is very handy, and we're looking forward to getting this through the pipeline. The thing here is actually the thing I mentioned is this is really nice because you can commit these things into version control, which takes Bender and the whole package management out of the EDA loop. Because the last thing you want is, in the hassle of a tape out on someone else's machine somewhere down the road, stumble because you cannot resynthesize stuff because you don't have the tool installed. But all the source files are still the same. And this also makes it easy to share work with other people which don't have the Bender tool installed. There's also other things. There's plugins, etc., which you can use. Which basically allow you to add custom snippets of tools, which are presented to the user as a kind of sub-command for Bender. Then there's some future wish list about testing, etc., which I will gloss over now, which basically will allow you to do kind of a turnkey solution for testing and integrated testing for CI, for example. All right, so this registering we skip. What happens if you hate this tool? There's other options available. There's, for example, Bazel, which has a cool layer which is kind of agnostic to what you're actually building, so you can use this to collect your RTL. Then there's the award-winning FuseSock, which can be used, which kind of ties into this, and there's also cool ways how you can make the tools collaborate on that. Other package managers like NPM, there might be options to integrate these things. There's some future work to do, Edelweiss integration with FuseSock, etc. But in conclusion, Bender is basically here to help you. We try to be as unintrusive as possible into your workflow. These are the things we tick off, and it would be really nice if you check it out, get in touch, give it a shot, and come up with your patches. Things are available here, repositories here, and thanks a lot for listening. I'm happy to take any questions.
So I think we have time for one or two short questions. Let's start here.
I notice in the Ariane repository, you've got like a common cells directory in the main thing and also a separate one in the FPU. Isn't that kind of undesirable to have multiple files with the same name, the same contents in different areas of the tree? Was that caused by Bender?
No, that's actually that's a kind of a relic. When we're doing some Bender development, there were times when we had, for certain sub-projects, we wanted to have a just flattened out version of the source files. So that was actually a deliberate choice, and this is obsolete now, and we're actually in the process of getting rid of that. But this was a transient thing that we did. It was a hack basically to add some of the submodules in as Git submodules. But this is what we're removing now because it's not needed actually.
So could you add a deduplicate function to just check that that's not happening? Because people can just edit one file and they edit and edit and edit, nothing changes. They don't realize there's another file which is the one actually being used.
Yeah,
different place.
That's a big problem of the way the EDA tools work. It's kind of this additive, sticky, last one wins scenario where you can have multiple files which override each other implicitly, right? So this is actually quite hard to check because you need to understand a lot of the semantics of the files themselves to check if there's some overriding happening inside the files. So here we actually leave this a bit as an exercise to the IP user, which is kind of the cheap way out. But if we had tools which could understand some of the semantics inside the system Verilog file, you could, for example, make sure that none of the IPs declare modules which overlap, or you could prefix a namespace, your IPs, for example. But it's not that trivial because it usually doesn't boil down to just replacing module names. But there's a lot of effects that kind of ripple through the source space if you do that. So it's pretty tough to get right. It's easy to hack, but hard to do right. So.
Thank you. If we don't have any very pressing question, a short one.
So I saw you're adding the scripts, and you mentioned it's getting the EDA out of the loop. I don't know if I caught it. Do you have the specific revisions or versions of the EDA releases to be recorded as well? That actually needs to be done as well, because you never know what's going to happen in a given release if you want to absolutely reproduce everything.
That is actually a very good point. So this is something we don't do at the moment. So basically we generate scripts, and the scripts are very minimalistic. So we basically try to only deal with the very front of the whole tool flow. So basically getting things into your synthesizer or into your RTL simulator. But we don't touch other parts of the flow, like constraints down the road or other ways of dealing with that. So we found these things to be fairly stable across tool versions, because it's basically just, you know, analyze this, analyze that, and this doesn't tend to change a lot. But you're right, to make it truly reproducible, if we would touch other parts of the flow, we would need to record that as well. This might be something where also Edelweiss can come in a bit more, right? Because this could cover other parts. Yeah, I fully agree.
I got the same question yesterday for FuseOC, and I think it's not enough, because we need to version the whole environment. I have had projects where changing the C library, and suddenly the CRC doesn't work. So you are absolutely right, but it's not enough.
Okay, thank you.
Thank you.
Thanks, Fabian.